two preparations. I'm still not prepared for quiz 1 year, honestly. I haven't even started. I'm just starting today.
We are not started.
Do you think, Jagan, we love you, but we don't believe you?
Don't tell my name again and again. Professor is joining.
Hello. Good evening to all.
Good evening, sir.
Good evening,
Good
sir.
evening, sir.
Good evening, sir.
Good evening, sir.
Am I audible?
Yes, sir.
Yes, sir.
Okay, fine. Okay, could you see my screen?
Yes, sir.
Please answer your
Yes, sir.
questions. Aditya Kumar,
Present, sir.
Anand,
Present, sir.
Ananta Kumar,
Present, sir.
Arnachalam,
Present, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Roshan Kumar,
Yes, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus, Valish, Vigneshwaran,
Present, sir.
Vijayaraj,
Present, sir.
Vikash,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj.
Present, sir.
Okay, Titus and Valish are absent today. Okay, I hope they don't have any problem with the audio. They are not here. Okay. So as I informed to you, it's always better to inform me if you are taking any leave. So for my record, so that it will be easy for me to follow up with you. That's one thing. And second one, the remaining materials for chapter 2, I have sent to you by today. So you know, Saturday you have your quiz 1 exam.
Yes, sir.
Okay, so for quiz 1, the people here in Chennai are going to come to IIT Madras. The venue for the exam is Diesel Hall in IC Engines Laboratory. Okay, and the exam starts by 10 o'clock. It will be for 50 minutes. The questions will be asked for 30 marks. You have to answer all the questions. There are no choices. 30 marks questions will be asked. Come with your calculator for the exam. Calculator is required. Chapter 1 questions will be based on the concepts, theory questions based on the concepts discussed in the class. Chapter 2, it will be problem based. So come with your calculator. Okay, so it is for 30 marks, 50 minutes is the timeline. You have to answer all the questions in 50 minutes. So in a relative grading system, generally the way we filter out S and A grade people are, you have to respond quickly. That depends on the time and effort you put in to prepare for the exam. Okay. So if you put more time and if you spend time for the exam for preparation, it will show up. Okay. There is no other way. So you have to respond quickly within the 50 minutes. Okay. Because it's not, your grades are not based on absolute marks. It's based on relative marks. How well you are doing compared to others is what will decide your grade. Okay. So you need to prepare for that. And the other thing about the people who are taking exam in Pune, TCS has denied conducting exam this time. I don't know the exact reason, but I tried to reach them and ask them to arrange. Somehow they denied. And so for 3 of you who are in Pune, Roshan, Ramanand and Yadav, right, Am I correct? So for three of you, the exam will not be in TCS. It will be conducted online. I will send you the link for the exam. You have to join online. I'll send the question paper just before the exam. You have to switch on the video. Okay, and you cannot have a blurred background. You need to switch on your video. Video should be on during the entire duration. I will have to monitor the exam. Okay, to maintain the integrity of the exam process, I need your cooperation. Ensure that you have a good internet connectivity and see that your video is on during the entire period. So for three of you, it will be online mode. I will monitor the exam, and for the rest, you have to come here and take the exam. Are there any questions?
Anything apart from that, calculator, stream table, anything we have to get?
No tables are required. I will provide whatever data you need. No need to bring any table. Only calculator is required. If you have an ID card, you have to produce ID card for the exam. That is also mandatory as per the institute norms. You all have been provided with an ID card, institute ID card.
Yes, sir. Yes, sir. Yes,
Yeah, it's better you bring it, especially you have to show it in the entrance also. So come with your ID card for the exam. If you have any other questions, you can, if there are any doubts while preparing, you can always write to me. I'll get back to you. Okay, so are there any questions related to the exam?
No, sir.
There are no questions. Okay. Okay, while preparing for the exam, if you have any doubt, you can write to me. I see few of you are leaving the class after the attendance is over. That is not the right practice. I would like you to remain in the call. Okay, so this is class. You cannot go out at any time. Please note. So once you join, you have to be there for the entire duration of the class. Please don't attend the class just for attendance. So I saw two of you have left the meeting. So
sorry, sir. It is because of network error only. My call got disconnected, and I rejoined again, sir. Sorry for that.
Okay, so you are not in the industry. You are joining through your personal network.
No, sir. I'm in office only.
Okay.
Because
in the
of
industry
some server
itself, there
issue.
is a problem. See, that is again a responsibility of your admin. There is any connectivity issue, they have to take care. Okay, it's part of the protocol that is already circulated to you people. If there is any such internet network issue, if it disturbs your regular attendance for the class, you let me know. You should let me know. I will try to resolve it. That's not even your responsibility because that's beyond your control, right? So if there are any such issues, you let me know. And other than that, I would like you to be there for the entire duration of the class. Please don't leave the class after the attendance or in between the class. That is not the right practice. Okay?
Yeah, definitely, sir. We'll ensure that.
Okay. Thank you.
Sir, Hemant was not there during the roll call.
No,
I was there.
The people who are absent are Vallis and Titus. Two people were absent.
Okay. Yes, sir.
Fine. Thank you.
Thank you, sir.
Okay, so welcome back. We are now in chapter 3. Okay, chapter 3 is about the actual SI and CI engine combustion. These are the contents we are going to discuss in this chapter. I provided an overview, just a quick recap. In this chapter, we are going to discuss about SI and CI engine combustion. I'll start with the overview of combustion process, and then I will discuss about the stages, different stages of combustion in SI and CI engine. Okay, so here we are characterizing the combustion event in terms of number of stages that the combustion event undergo. The purpose of characterizing the combustion event is to have a better control over the event, because we need to control the combustion event because it is predominantly affecting the engine performance as well as the pollutant that are emitted from the engine. Both engine performance and pollutant emissions are affected by how well the combustion event progresses. Okay, so we need to control this combustion event from the perspective of improving engine performance and reducing the pollutants that are emitted from the engine. So that's why we are characterizing here the combustion event and then we will talk about the various factors that affect different stages of combustion. When I say factors influencing combustion, it refers to engine design based factor or engine operating variables that affect or influence the combustion event. So you need to have an improved understanding about the various engine design and operating variables that affect this combustion event, progress of combustion event. Once you have an understanding about these variables, you can handle them effectively so that the combustion can be better controlled, so as to improve the performance, engine performance, and so as to reduce the pollutants that are emitted from the engine. Then we will talk about abnormal or knocking combustion. This is one of the undesirable phenomena with regard to combustion. We want to avoid it because this may lead to damage, engine damage in the worst case scenario. So we will here discuss about the mechanism behind the occurrence of knocking or abnormal combustion, and then we will see how we can avoid such occurrence, how we can avoid abnormal combustion. We will discuss what are the factors that we can utilize to avoid abnormal or knocking combustion in engines, SI and CI engine. Finally, we will discuss about the combustion chambers for SI and CI engine. Combustion chamber is a location where the combustion event is happening. There are different designs of combustion chamber, and this design, combustion chamber design, is going to affect this event, progress of the combustion event. So we'll talk about the designs, available design of combustion chambers for both SI and CI engine. So the way I will handle this chapter is I will start with spark ignited engine combustion. I will follow this sequence of contents, and then I will start CI engine, compression ignition engine combustion. Same sequence of contents will be followed, okay, for diesel engines. So I'll start with the overview here, overview of spark ignited engine combustion. So as I just now said, this combustion event affect the performance and pollutant emission. So when we do research on engine, we have only two targets. One is engine performance improvement. That is, we want to achieve the desired power, torque output with minimal fuel consumption. As you know, as an end user of vehicle, one always worry about the mileage it gives, right? The consumption of fuel is what is of primary importance for the user, end user of the vehicle. So you need to ensure that the engine is performing well in terms of producing the desired rated power output with minimal fuel consumption, right? We also want to ensure that the pollutants emitted from the engine are minimal. Otherwise, you cannot sell the vehicle as an engine OEM. Okay, so this is a legal requirement. Pollutant needs to be reduced below the current legal limits. So we always have this two target, performance improvement and pollutant reduction. To achieve this, we need to handle this combustion event effectively. We need to control this combustion event effectively. Ignition timing is the time at which the combustion gets started, and the other one is combustion phasing. Combustion phasing here refers to how well you are placing the combustion event with respect to engine operating cycle. So you know, for one engine operating cycle, there is a finite duration. This finite duration of engine operating cycle depends on the engine running speed. I think I already said about it. So this is engine cycle time. This engine cycle time depends on engine running speed. When the engine runs at very high RPM, the cycle time is going to be less. So when I talk about combustion phasing, I'm talking about where we are placing this combustion event. So combustion event also takes a finite time defined by combustion duration. So when I talk about combustion phasing, I am talking about where I am placing this combustion event in the engine cycle time. Okay, whether it is here or here or here, this is what I mean by combustion phasing. This is very important, right? When I talk about combustion control, you need to control this combustion phasing effectively. Otherwise, you cannot maximize the performance or you cannot reduce the pollutant. Untimed energy release is of no use. You will lose power, engine power will be lost, and fuel consumption will be very high. Untimed energy release will also lead to very high pollutant level. So the combustion event has to be effectively controlled in terms of controlling the start of combustion. In a spark ignited engine, you control spark discharge. By controlling spark discharge time, you are controlling ignition timing. In a CI engine, you are controlling ignition timing by controlling the fuel injection timing. Okay, so you have an external control to better monitor and track the timing of ignition based on the engine running condition. In a SI engine, you do it by controlling the spark discharge time. In a CI engine, you do it by controlling the fuel injection time. So this is one of the important variable, combustion variable that needs to be controlled. The second important variable is the phasing of combustion with respect to engine cycle time. These two needs to be closely controlled in order to achieve better engine performance and pollutant emission. So the overall takeaway for you is we need to have an improved understanding of combustion event, and we need to control this combustion event so that we can maximize engine performance and minimize pollutant emission. Now, to initiate the combustion event, both in SI engine and CA engine, there are two requirements that needs to be met. The first requirement is you need to have an ignitable mixture. Fuel and air cannot ignite at any proportion. You need to have a finite proportion of fuel and air, then only it can ignite. That finite proportion of fuel and air that undergoes combustion is referred to as ignitable mixture, defined as equivalence ratio with a subscript IGN is for ignitable mixture. So you need to ensure that you have an ignitable fuel air mixture inside the cylinder. Without this, the combustion event cannot get started. The second requirement is you need to ensure that there is an ignition source. There is a thermal energy available defined as T with a subscript ignition. There is a thermal energy available to initiate the combustion. In the previous chapter, when we discussed about kinetics, I told you that we need to overcome the barrier, chemical energy barrier, which is defined as activation energy. You have to provide activation energy in the beginning to initiate the radical formation. Once the radicals are formed, the combustion event will go on its own. It's self-sustaining. But you have to start the process. Okay, you have to start the process by providing thermal energy. Then the process is exothermic. It is going to release the thermal energy once it gets started. Okay, but you need to initiate it. So there are two requirements here. One, presence of ignitable mixture. Second one, there should be ignition source. Here you should also note that it's a combination of these two. Suppose if you have an ignitable mixture and if you don't have a thermal energy to initiate combustion, the combustion is not going to happen. You have enough thermal energy, but if you don't have a ignitable fuel air mixture, the combustion is not going to get started. So it's a proper combination of this P ignition and T ignition. That is what is going to initiate the combustion event. So this is an important point you need to note down. Okay, that is how the combustion event get initiated both in SI engine as well as in a CA engine. Now coming back to spark ignited engine, which is what our focus now, and then we will move on to CA engine combustion. In spark ignited engine, when you talk about the mixture preparation, I need to have a ignitable mixture, right? How I am getting this ignitable mixture? The strategy adopted in SI engine to prepare an ignitable mixture is referred to as external mixture preparation. What is external mixture preparation? Fuel and air are prepared outside the engine cylinder. The ignitable fuel and air are prepared outside the engine cylinder. This is contrary to what we do in a diesel engine. In a diesel engine, fuel and air are prepared inside the combustion chamber where the ignition or combustion is happening. Okay, that is referred to as internal mixture preparation. Here in a SI engine, you are introducing fuel outside the engine and fuel and air is injected outside the engine. So the mixture, fuel air mixture is prepared outside the engine. That's why it is referred to as external mixture preparation. How this is done? This is done by using device, either a carburetor, which is still used in very low cost SI engine. It's generally outdated now. Okay, so we mostly use a port fuel injection system to introduce or inject fuel into the engine intake system near to the port. That's why it is called port fuel injection system. I'm not going into details of the engine system. Our focus here is on the process, combustion process. Okay, so I will briefly discuss about the system that are used to prepare mixture. Okay, just for the purpose of understanding the process. Carburetor is still used in very, it has very limited application only for low cost engines. This is still used in some other engines. It's still used, but it's mostly port fuel injection system where the fuel is sprayed. Okay, near the intake port. Near the intake port, the fuel is sprayed, and that is how. So this is intake port or the region where the air fuel mixture is entering into the engine cylinder. Here you have air coming in, injected through the intake manifold. Okay, port fuel injector is located here. It sprays fuel over the port, intake port. Okay, and thereby it mixes with the incoming air, and fuel and air mixture is entering into the engine cylinder. So mixture is introduced outside the engine. Fuel is introduced outside the engine. Mixture of fuel and air is what is entering into the engine cylinder, the ignition. Okay, so that's why it is referred to as external mixture preparation. Carburetor, although cost is low, you cannot have a precise control over fuel air mixture. It's a kind of inaccurate way of preparing fuel and air. You cannot precisely meter the fuel proportion, right, with the help of a carburetor. PFI system, port fuel injection system, is more precise and accurate, but the cost is high. So current engines mostly use this port fuel injection system, wherein you spray fuel over the intake port, which mixes with the incoming air and enter into the engine cylinder. So that is how we prepare this fuel air mixture. The two important points that you need to note down are, when do you inject the fuel in a SI engine?
During the suction stroke.
During the suction or intake stroke. So fuel is introduced during the intake or suction stroke. So what is the time available for mixing?
TDC to BDC.
Okay, the entire
Yeah.
the entire intake stroke is available. When do you discharge electric spark?
At the TDC.
Near TDC during the
end of compression.
End of compression.
End of compression. So end of compression is the time when you discharge electric spark through a spark plug. So here you have a spark plug. You are discharging electric spark near the end of compression stroke. Okay. So the time available for mixing T with the subscript mix is the entire intake stroke and almost entire compression stroke. 360 degree, right? If you take one stroke, one complete stroke, it's around 180 degree in terms of crank angle time, that you can convert it to absolute time. We do analyze all the events only on a crank angle base. Time is analyzed in crank angle, not in absolute time unit, because there is a reason. I will discuss about that. So the time available for mixing here is the entire intake stroke as well as the compression stroke. It's almost 360 degree time you are giving for fuel air mixing. Okay. Because of this reason, you have a homogeneous mixture. You have a homogeneous mixture in a spark ignited engine. It's also referred to as homogeneous combustion. The mixture is homogeneous for two reasons. One, you provide a very high time for mixing, fuel air mixing. This is again contrary to what we do in a CI engine. You inject fuel near the end of compression stroke. So the time available for mixing is very few degree crank angle. Here it is almost 360 degree crank angle. Do you understand? So that's why you end up in preparing heterogeneous mixture in a CI engine. Here you have homogeneous because I provide more time for mixing. Point number one. Point number two, the fuel. What type of fuel we use here? Gasoline or petrol. And in terms of fuel characteristic, we already discussed this in chapter 1. What type of fuel is gasoline from the mixing characteristic point of view?
It is volatile and it should be aromatic content. So it's very
volatile. Okay. So from the mixing perspective, volatility plays a big role. When I say fuel is highly volatile, it means it can readily vaporize and mix with air. That is what I mean by volatility. Okay, that's a physical meaning. So gasoline is what is the fuel that I use here, and this fuel is highly volatile, meaning it can readily vaporize and mix. Okay, the combination of these two factors. One, I provide higher time or longer time for mixing fuel and air. Second point, I have a fuel gasoline, which is highly volatile, which can readily vaporize and mix with air. Because of these two reasons, I end up in providing a homogeneous mixture just before ignition. The mixture that I prepare in a SI engine is homogeneous. When I say homogeneous, it is homogeneous with respect to space and time. What do you mean by homogeneous with respect to space and time? Inside the engine cylinder, everywhere the phi value is going to be constant. This is what I mean by homogeneous. And with respect to time, the mixture is homogeneous, meaning with the variation in crank angle also, time here is specified in terms of crank angle. With variation in crank angle also, the mixture proportion is not going to change. So I have a phi value which is homogeneous in space, I mean inside the cylinder, everywhere it is same. The mixture is also homogeneous with respect to time, meaning with respect to crank angle variation, the mixture proportion remains constant. So SI engine, because of external mixture preparation based strategy, I end up in forming a homogeneous mixture, homogeneous fuel air mixture, which is not possible in a CI engine. So that is how I get into this ignitable mixture in a spark ignited engine. Using an appropriate device and external mixture preparation based strategy, I provide a homogeneous fuel air mixture, ignitable mixture to the cylinder. Then how do I get the ignition source? That is point number 2. Ignition source is provided by discharging electric spark. Okay, discharging electric spark provides a very high thermal energy, T ignition. This helps me in forming radical to initiate the combustion event. I have a homogeneous mixture prepared through external mixture preparation strategy. Now I am discharging electric spark to this homogeneous mixture, okay, to initiate radical formation to start the combustion event. Okay, that is how the combustion event gets started. I have a combination of these two in a SI engine. That is how I get started with the combustion event. Once the spark is discharged, once the ignition happens, so what will ultimately result is a flame. A flame will form around the spark plug region, okay, and this flame has to be a stable flame. Otherwise, the combustion will get started, but it cannot continue, okay, it cannot continue or sustain. So you need to ensure that the flame formed around the spark plug region is stable. Once you ensure that the flame is stable, then the stable flame will propagate across the combustion chamber and it is going to burn the unburned fuel air mixture that resides in the combustion chamber. I form fuel air mixture around the spark plug region. So around the spark plug region, by discharging electric spark, you are creating a stable flame and this flame propagate across the combustion chamber. And in the process, it is igniting the mixture, unburned mixture that resides in the engine cylinder. So I have shown here in a side view. So you could see that there is a thin flame that propagates across the combustion chamber with a velocity. That velocity is referred to as normal flame velocity. The velocity at which the flame moves in a direction normal to its surface is called normal flame velocity. So the flame moves with some velocity defined as normal flame velocity, and once the flame gets formed, you have two regions in the combustion chamber. One is called burned region, wherein you have burned gases behind the flame front. The second region is the unburned region, wherein you have unburned fuel air mixture that is present ahead of the flame front. So flame is dividing the combustion chamber into two regions. One is a burned region behind the flame front, other one is unburned region ahead of the flame front. Now the flame is moving with some velocity defined as normal flame velocity and ignite this unburned mixture. As I have already told you, at any point of time, the unburned mixture has to be ignited only with the aid of flame. The mixture should not ignite, self-ignite, meaning the mixture should not ignite by itself. Once it self-ignites, what is that combustion event?
Knocking, sir.
Knocking or abnormal is nothing but self-ignition of this unburned mixture. At any point of time, only the flame has to ignite the mixture. Okay, this is a normal combustion event in a spark ignited engine. Now, when you look at this flame velocity depends on both physical process as well as chemical process. I have highlighted here what are those physical process. Okay, and I have put a plus symbol here, meaning that these two processes are coupled. You cannot separate one process from the other process. These two are interlinked, coupled. Okay. Physical process here refers to heat transfer from the flame zone or reaction zone. There are different modes of heat transfer. Predominant mode in an IC engine combustion is radiation mode because there is less time and the flame is at a very high temperature. Okay, due to which it radiates thermal energy. There is a radiation of thermal energy from the flame zone to the unburned mixture. So there is a heat transfer. There is a mass diffusion that happens due to concentration gradients. Between the burnt and unburned region, there is a concentration gradient that helps in mass diffusion. Okay, that happens between these two regions. Any concentration gradient will result in mass diffusion according to fixed laws, you know. So there is a mass transfer that also happens during this period of time, which is a physical process. The third one is fluid dynamics. The fluid dynamics in the combustion chamber is also a physical process. Fluid dynamics here refers to how quickly the flame moves with respect to design of the combustion chamber. That we are going to discuss in the last part of this chapter. We are going to see how the combustion chamber design affects the flame movement. Again, it's a physical process. The way you shape the combustion chamber, especially the piston crown, that's the top portion of the piston, and the cylinder head. The shape of the cylinder head and the shape of the piston crown will create fluid dynamics inside the combustion chamber. Later on, we are going to see about this. Okay, that will affect the flame velocity. The flame velocity is also affected by the chamber design. So these are the physical process that happens during the flame movement, which are affecting the velocity of the flame. The chemical process here refers to the kinetics, chemical kinetics in the flame zone. Flame zone is also reaction zone. This is where the combustion event is happening. Flame zone is where the combustion event is happening. This is also called reaction zone. Okay, and the rate of combustion is governed by kinetics. We already discussed previously in the chapter 2. Kinetic rate is dependent on the molecular composition of the fuel. Okay, so this is primarily dependent on fuel molecular composition. So there is a physical process, there is a chemical process, and these two are combined because the rate at which the heat transfer happens will affect the rate at which the kinetics happen, because kinetic rate is highly sensitive to temperature and heat transfer affects temperature. Mass diffusion affects mixing of fuel and air between the two zones. Okay, that again affects the chemical kinetics. And design of combustion chamber affect the flame movement. The flame velocity also affect the rate of combustion. So these two are intercoupled because kinetics also, the thermal energy released during combustion, since it's an exothermic process, the temperature will start to rise. With the increase in temperature, heat transfer also increases. You could see that these two processes are coupled. Okay, and that is how the flame is moving in the combustion chamber, inside the combustion chamber of SI engine, and which is what is affecting the progress of the combustion. So we can say that the overall combustion event in an SI engine is a flame propagation based combustion event. Flame propagation based combustion event, okay, based on which the thermal energy release is happening, meaning the rate at which the thermal energy is released is dependent on normal flame velocity, which in turn is dependent on physical as well as chemical process. So this is how a combustion event is happening, and the combustion event will continue to happen as long as you have a stable flame. And once the flame get quenched, the combustion event will get stopped. And this generally happens when the flame reaches the corners of the combustion chamber. When the flame reaches corners of the combustion chamber, there will be heat loss from the flame zone. Can you tell me the condition based on your understanding? Can you tell me the condition at which the flame will get quenched? There is a thermal energy release happening here in the flame zone. Okay, after some time, the flame is going to get quenched or extinguished. Then there is no combustion. When do that happen?
If it's a too rich mixture.
Okay, so with respect to mixture condition, when it is too rich, you cannot maintain a stable flame. Okay, anything else?
Sir, when it is hitting the wall of block and I would sacrifice volume.
When it reaches the corners, it cannot move ahead and it will get quenched. Okay.
Sir, complete consumption of fuel.
Okay, once all the fuel is consumed, there is no more combustion event. Okay. Anything with respect to energy balance?
When the heat of formation is completely released from the fuel.
So what will also happen is heat loss, Q loss. Okay. So there is a Q generation due to combustion event. There is a Q loss because you don't have an insulated system. Right, you have a system that is exposed to ambient. Engine surface is exposed to ambient. So always there is a heat loss. So what is also simultaneously happening during the combustion event, flame is generating heat because it's an exothermic reaction. What is also happening is the loss, heat loss, because surrounding temperature is less. Always there is a temperature gradient that enable heat transfer. There is a delta T between the combustion region and outside the combustion region where you have a lower temperature. So this delta T is driving this heat loss. What will happen after some time, the heat that is generated will be slowly start to decrease when the flame reaches the corners and the heat loss is going to dominate. It is going to increase. Okay, once the heat generated balances the heat that is lost from the flame zone, the flame cannot sustain. Please note that the heat generated should always be higher than the heat that is lost. Once these two are balanced, the flame cannot move ahead and the flame will get quenched or extinguished. Okay, that is a condition, acute condition for the end of combustion. Okay, the flame cannot sustain after some time because of higher heat loss. Is it clear? So this is how the combustion event is happening in a spark ignited engine. This is an overview of combustion event. Now we are going to discuss about the stages of combustion. So we are characterizing the combustion event in terms of number of stages. The purpose here is to control the combustion event after characterizing this. Now let us look at the stages of combustion event. So this stages of combustion event is explained with the help of pressure crank angle diagram. In shorter form, it is called P theta diagram. P is pressure, gas pressure inside the cylinder, and theta is crankshaft angular position. Theta here refers to crankshaft angular position. Can anyone tell me why we are not analyzing combustion event with respect to absolute time? I said that this is an indicator of time. So we are analyzing how the pressure in the cylinder varies with respect to time in terms of crank angle.
Because combustion is always defined with respect to piston. And since the
RPM. It's invariant of the RPM.
It's a variant of RPM, engine running speed. Fine. Yeah, it is fine. So you could see that pressure is on y-axis and the angle, crank angle is on x-axis. That is theta. Okay. TDC point is compression TDC. Angle is 0 degree. On the left side, you always indicate with a negative sign minus 180 degree. On the right side, you indicate with positive sign plus 180 degree. This is a standard nomenclature. This is the region where the combustion is happening, right? That's why this is a reference point. TDC is a reference point, and this, you know, piston reaches TDC twice in engine cycle, and we consider compression TDC as a reference point, not the other TDC. Okay, because that is the region where the combustion event is happening. So from analyzing the combustion event, from the perspective of analyzing combustion event, the compression TDC plays a significant role. That's why this is taken as a reference point. At that point, it will be considered as 0 degree. Once you move in this direction, which is compression process, okay, here it is referred with the negative sign, meaning that the piston is yet to reach the compression TDC position. That's why you are indicating with the negative sign. Once you move toward this region is an expansion region. So you indicate crank angle with a positive sign. This is a standard nomenclature. We use negative sign to indicate angle during compression process and positive sign to indicate angle during expansion process. So we are analyzing how the pressure varies in the engine cylinder with respect to crankshaft angular position, because the engine we are talking here are reciprocating engine. In a reciprocating engine, as you know, in a reciprocating engine, there is a slider crank relation that comes into picture. Okay, so we have a piston here. This is TDC, compression TDC. Let us say the piston is moving up during compression process. Okay, you have piston here, and any instantaneous position, this is a particular position of the piston, say X. Okay, and then you have a connecting rod and crank here. So this is the angle we are talking, crankshaft angular position theta, and there is a linear piston position X. For any, this theta and X are interrelated through slider crank relation. Because it's a reciprocating engine. Piston reciprocate, it moves up and down, and crank rotates. And there is a relationship between this linear motion and rotary motion. Okay, that's why I say that for each theta there is associated x. X means instantaneous piston position. So we analyze time in terms of angle, crankshaft angular position, because crankshaft angular position provides me information about the piston linear position in the cylinder. Okay, for any theta, instantaneous theta, there is an instantaneous x. So meaning I am analyzing how the gas pressure varies in the cylinder with respect to the position of the piston. This is an important point. If you analyze pressure variation with respect to absolute time, it doesn't make any sense because it completely misses out the information related to piston position. Here I am with theta, I am analyzing gas pressure variation with respect to piston position, because I need to know where the piston is at a particular magnitude of the gas pressure. I need to know where the piston is. For example, at the start of expansion process, I need to ensure that I have a maximum pressure here, then only I can recover maximum work. Otherwise, it's of no use. If maximum pressure occurs during compression stroke, I cannot recover that as a useful work. Okay, it has to happen during the expansion stroke. That's why it becomes important to analyze how the pressure varies with respect to piston position. That is the reason why I always analyze combustion even with respect to crankshaft angular position rather than absolute time. Absolute time completely miss out the information related to the piston position. So here we are going to discuss about the different stages of combustion. Okay, basically we are characterizing the combustion event in terms of the stages that the event undergoes. And this is explained. First, let us start with the theoretical pressure crank angle diagram. In the theoretical pressure crank angle diagram, you know that SI engine combustion is what type of combustion event? SI engine combustion. You have studied in thermodynamic cycles. SI engine combustion is modeled
Constant
as
volume, constant volume.
constant volume. So it is Otto cycle. So it's a constant volume combustion. So here I have indicated that as a theoretical process. So it's a theoretical pressure crank angle diagram associated with the constant volume combustion in SI engine. So you could see that the pressure profile, pressure crank angle diagram is also called pressure profile. The pressure profile will look something like this. You have compression event, pressure increases, and then there is a combustion event, which is constant volume, meaning entire combustion event is occurring when the piston is at top dead center, compression TDC. When the piston is at compression TDC, you have the entire combustion process happening. So you have a vertical line here. Then there is an expansion process. Okay, the pressure drops linearly during expansion process because you are recovering the energy release into work. Because of work recovery, there is a drop in pressure and the piston is moving down. Okay, so compression, the piston is moving up. And during expansion, the piston is moving down, and the reference point for me is TDC. And I'm assuming here in the theoretical process, constant volume Otto cycle process, I'm assuming that the entire combustion event happens when the piston is located at the compression TDC point. So you have a vertical line here. There is a sharp rise in pressure because there is an instantaneous energy release. This is a theoretical diagram according to Otto cycle where the energy release happens at constant volume. Now, what problem will be encountered in a real engine? If this happens, you will have a maximum work that can be recovered from the engine because the pressure magnitude will be very high. During expansion, you can recover maximum amount of work if this happens. Okay, that's why theoretical process always gives you the direction for achieving maximum work. But there is a problem. We cannot have a pressure crank angle diagram like this in a real SI engine. Can you highlight what problem will happen if this happens in this?
Durability, sir. Durability of the component will be very much shortened in that way.
What is it? Variability?
So durability, sir. Durability.
Durability. Okay, durability will be shortened. Okay, anything else?
Sir, if I'm not wrong, if I understood your question properly, like you mean this is ideal and this will not happen in real life?
Real engine, yes.
Because there will be a combustion delay. The pressure will not go to top in the y-axis, right? Like it will take some time, and there will also be due to improper combustion. There will be some spikes here and there during the.
So actual combustion, you are saying that it will take time.
Yeah,
It will be instantaneous.
Correct.
But you can always make it instantaneous, right? That is how explosion is happening.
Okay.
It's almost like explosion, sir. Rate of pressure is.
So we discuss when we discuss about kinetic, there is something called chain branching. I discuss, right? Chain branching reaction.
Yeah.
Chain branching reaction will increase the radical pool. A bomb blast is happening primarily due to chain branching reaction. All the reactions, most of the chemical reactions will be dominated by branching, meaning you are building a radical pool in short time. Because of high radical concentration, all the energy will be released instantaneously. Because once you have sufficient radical, they don't need any further energy, activation energy to progress. Okay, they have enough. They are highly unstable. They combine and release thermal energy in no time. This is like an explosion, right? Constant volume combustion. We don't want this to happen because it will damage the engine. We don't want an instantaneous combustion, although thermal efficiency is going to be high. This is going to damage the engine. So what I want instead is I want a progressive combustion. I don't want instantaneous combustion. I want progressive combustion. Instantaneous combustion will give high thermal efficiency, but it will damage the engine. Okay, and also there will be discomfort. At a low minimal effect is discomfort. Vibration will be high, noise will be high. This is what I mean by discomfort. You know, there is a NVH characteristic that also needs to be met, right? When you design the engine, this will be very poor if the combustion event is instantaneous, and the magnitude of this problem will be severe when you are burning more fuel air mixture as compared to burning less fuel air mixture. So what I want is progressive combustion. I don't want instantaneous combustion. That's why the actual pressure crank angle diagram will be something like this. Okay, so here A is the point where the spark is discharged. That is where you are initiating the combustion, and D is the point where the combustion gets stopped. Okay, so you could see that there is a considerable period taken. The combustion is not instantaneous, vertical line. Rather, it is happening during a considerable period of time. This is duration of combustion. Combustion is happening during a considerable period of time rather than instantaneous. This is what I mean by progressive combustion. Combustion happens progressively in 3 distinct stages in a SI engine. Those stages are indicated here. Stage 1 is from A to B. Stage 2 is from B to C. And then you have stage 3 that is from C to D. There is stage 1, stage 2 and 3. So actual combustion event in SI engine takes considerable time as indicated here, and it happens in 3 distinct stages as indicated in this pressure profile. So here also I have used pressure in y-axis. What do you have on x-axis is crank angle theta. So this is crank angle in degrees. Okay, and in y-axis you have pressure generally indicated in bar. I'll talk more about it as we move on. And this side is the compression region wherein you indicate crank angle with a negative sign, -60, -40, -20. And this side is the expansion process. This is expansion. This is compression process. Expansion is indicated with positive sign, 20 degree, 40, 60 degree. So you could see that combustion event happens during considerable period of time. It's not instantaneous or constant volume. It happens over a period of time. Okay, and that is indicated in this is the actual pressure crank angle diagram. It's also called pressure profile. So this is how the actual event happens. Here I have 2 profiles. One is called motoring pressure and second one is firing pressure. What is this motoring pressure?
When there is no ignition or spark provided.
Yes,
That's
so
the pressure filter.
this is without spark. Without spark discharge. If you don't discharge electric spark and if you just compress, okay, you will have a profile like this. Okay, when you don't discharge electric spark, there will be compression, there will be expansion, but it is without firing, without combustion. That is what you are getting here in dotted line. This is a profile you will get, all right, when you don't discharge electric spark. When you discharge electric spark, this is the profile you will get. It is called firing pressure profile, P theta diagram. That is indicated here in 3 finite stages, AB, BC, and CD. Okay, so what are those 3 stages? Stage 1 is referred to as flame development period. That is a period required to form a stable flame. Here you should note that it's not about forming a flame. The flame that is formed during this period of time should be stable. Then only the combustion event can sustain. Otherwise, the combustion event will get started, but it will stop. That is called misfire. In an actual engine also, you have come across this term misfire, right? There are misfire cycles that will happen. That is primarily because the flame that is generated cannot sustain. So you need to form a stable flame, and that is happening during this first stage. First stage involves forming a stable flame. That's why it is referred to as a flame development period. It's also called ignition lag. Technically, there is no ignition delay in SI engine, but what we refer here by saying ignition lag is the time that is required to form a stable flame. Second stage refers to flame propagation period or rapid burning period, because this is a period where most of the charge is burnt. Okay, most of the fuel air mixture charge here refers to fuel air mixture. Most of the charge is burned during the second stage. That's why it is called rapid burning period. It's also the period where the flame propagate across the combustion chamber. As I have indicated here, the flame moves with some velocity, right? And that is happening, the flame propagation is happening during the second stage. Okay, it's also called rapid burn period. The third stage here is referred to as the flame termination period or after burning period. This happens when the flame reaches the corners or boundaries of the combustion chamber. Okay, this stage 1 happens around the spark plug region where you are generating a stable flame. Stage 2 is the period where the flame leaves the spark plug, moves across the combustion chamber and burn most of the charge. So most of the charge is burned during the second one. The third one is the stage where the flame reaches the corners or boundaries of the combustion chamber. That is a region where, that is a time period where the heat loss will start to increase significantly because the flame has reached the cooler regions of the combustion chamber. So heat loss will start to increase. Finally, there is a stage where the heat loss balances the heat that is released, and because of that, the flame get quenched or the flame get extinguished, and the combustion event that marks the end of the combustion event. Until there is a flame, there is a combustion event. Once the flame get extinguished, there is no more combustion. And this happens when the flame reaches the extreme corners or boundaries of the combustion chamber. So that is how the actual combustion event will happen in 3 stages in a SI engine. I'll give more finer details about these 3 individual stages in the next class. I stop here. It's time up. If you have any questions, you can ask your questions now.
So one question regarding ethanol blending on gasoline, sir.
Okay.
Sir, if we blend ethanol into gasoline, is it like we should consider like it is like a catalytic polymerization and the alkyl will blend with the gasoline, or it will be 2 separate components and we have to write combustion equation separately? Sir?
No, the way the combustion happens is the combustion is happening with a blend, right? Proportion. So in an actual engine, if you blend gasoline and ethanol, okay, so you will have a blend. You are not mixing them. You are mixing them only physically, right? There is no molecular interaction as such. When you have a molecular interaction, then the molecular structure itself is going to be different when there is a chemical reaction. The way it happens here is with physical mixing. So you have gasoline, you have with a different molecular structure, ethanol single component with a different molecular structure. And these two are physically mixed by using a stirrer or whatever. Sometimes it is prone to phase separate because these two are immiscible. When you go to higher ethanol concentration, they will phase separate. Especially when ethanol is having water content, it will phase separate. Okay, so it is just a physical mixing. There is nothing happening at the chemical level. So energy release will happen with the blend, but this two fuel you can consider as an individual fuel that bonds. Since they are mixed physically, we are considering both when you write the chemical equation.
Okay, so is it like we have to write the equation separately and take cumulative effect of both those?
Yes, yes.
Okay. Sir, how will the combustion equation look for ethanol, sir?
Combustion equation in the sense, what you need to write combustion equation is only molecular formula. Ethanol formula is C2H5OH. So once you know molecular formula, you can write the combustion equation. Only difference here is ethanol is an oxygenated fuel. Unlike gasoline and diesel, which we have discussed in chapter 2, ethanol has oxygen in the molecular structure. So you have C, H and O.
Yes, sir.
Yes, Prem Vinayak, you have raised your hand.
Sir, if we have time, can we actually ask a doubt on, can I actually ask a doubt on the previous lecture?
Yes, yes.
Sir, this is regarding that molecular structure effects on CI engine and SA engine combustion. There were 4 graphs that was displayed in one of your lectures. Can we open that, sir, if that is possible?
Yes, this one.
Yeah, yes, sir.
What is your doubt?
I'm sorry, can we go to the previous slide also? Sorry.
Okay.
Previous slide. There was another graph, I think, sir. Sorry. Can we go to the previous slide?
This one?
No, sir. So the query is like this. So basically, there was a term called as carburetor icing in one of the graphs. I'm just trying to trace out that graph only.
Carburetor tracing is not here. It's
not tracing. Carburetor icing. There was
carburetor icing. Yes.
Yeah. So here, sir. Yeah. Fuel volatility characteristics. So
yes.
What is the meaning of carburetor icing, and if it is related to any low temperature things, why it is going till such a high temperature?
So carburetor icing is primarily happening due to water getting into solid phase. So when you inject air into the combustion, air into the engine, air has some, because of humidity, it has water vapor, right? Water vapor.
Understood.
And when you inject air from the surrounding ambient, air is injected along with the water vapor. It depends on the humidity level.
Correct, sir.
Okay, in Western country, this is applicable only for Western country, not for country like India where we have tropical climate. In Western countries, when you inject air with water vapor, okay, when the fuel vaporizes from liquid phase to gas phase, right? Combustion is a gas phase phenomenon. Liquid phase fuel is what is introduced into the engine. Yeah. Once the liquid phase fuel gets converted to gas phase, it absorbs the latent heat, right?
Yes.
As it absorbs latent heat, the temperature drops too low. Suppose if the intake temperature is too low, it may also lead to icing condition.
Okay, now it is clear.
So this is primarily because of the absorption, thermal energy absorption effect. Thermal energy absorption may also lead to icing if at all initial temperature of the air is too low.
Noted, sir, clear.
And this happens only in Western countries. Okay, in India, we don't have this problem.
So similar question on the same graph. T10, 50, 90, we clearly understand. What is meant by E200 and E300, sir?
This you can leave. This is not related to our discussion.
Okay, sir. Okay. So
for our discussion, you can focus only on T10, T50, and T90.
Noted, sir. Noted. Yeah.
Okay.
Thank you.
Sir, one more question on this.
It's taken from Chevron. Okay, so they have several other things which are not required for us.
Sir,
that's why I have not discussed this when I discussed about this plot.
Yes, sir. That's the reason why I just happened to ask the question.
So I thought it is not required for you. I don't want to discuss unrelated materials. Okay, that's why I skipped this part.
Noted, sir. We thought it might be something for the exam, so that's the reason why I was asking that. So.
Okay. Yeah. Anything else?
Sir, one question I want to ask. In the same slide, if you go to slide number, I think 14, if I'm not wrong.
14.
Oh, no, 13, sir, 13.
13, okay.
Yes, sir. Sir, you have taught us that the CN number of a fuel is dependent on how quickly it can form the radical, right, sir?
Yes.
So basically, you had also taught us that if the fuel composition is having ring structure, that is supposed to be more stable than the chain structure in that way. Now here, cycloparaffin is having a ring structure, whereas isoparaffin is having a branch structure. So, like what I mean to say, you had told something, but we have missed the link. Why the CN number of cycloparaffin instead of having a ring structure is better than what I mean to say is branch structure?
No, branch structure is also unstable. I mean, branch structure apart from ring structure is also stable. That's why you have a very low cetane number. Okay, very low cetane number. So this is also a very stable structure, branch structure. In fact, one of the important process in the refinery to improve antenna quality is catalytic reforming. If you remember, I said about
Right,
it, right?
sir. Right.
In a catalytic reforming, what they do is they will convert this chain into branch. Because you could see here that this is normal octane and this is isooctane. Both normal octane and isooctane are having same molecular formula C8H18, but the molecular structure is different. Here you have a branch structure, here you have a chain structure. These are chemically referred to as isomers. These two are isomers, meaning they have same formula but different molecular structure. Because of change in molecular structure, the cetane number is considerably reduced from 64 to 12.
Right, sir.
This is taken from a standard database where they have indicated the cetane number, but this also has some uncertainty. Okay, sometime the measurement of cetane number or estimation of cetane number will have some uncertainty. Okay, but this gives you the direction that when I move from straight chain to branched chain, the ignition quality is going to drop considerably. These two are isomers, but cetane number here is 64, here it is 12. So even it is lower than the ring structure as you have observed. Ring is also stable, but the branch is also very stable, which leads to very poor ignition quality.
So if someone is making a statement that any fuel which is having a ring structure will have lower cetane number is wrong, right, sir? It may be situational in that sense. What I mean to say.
No, generally ring structure will have a low cetane number. Branch structure will also have a low cetane number direction wise, but the absolute value depends on what hydrocarbon you are considering here. Did you see? This is only class. This is a base structure, okay? But in this class, you will have different hydrocarbon. Right, you may have C8, C6, or C4, whatever it is. The number of carbon and hydrogen atoms are going to be different. Only molecular structure is same, okay? Only molecular structure is same. The number of carbon and hydrogen atoms are going to be different. And this may also have a lengthy side chain, as I have indicated during our discussion on octane.
Yes. If we add lengthy chain, that will further
that will change the quality, ignition quality.
Right.
So what you need to take away from this is it gives you the direction. What will happen to ignition quality with respect to a particular structure. But in that particular structure also, there are n number of hydrocarbon that you need to understand with different carbon number and hydrogen number that will also have an effect.
Right.
So just to add upon Mr. Roshan's comments and to summarize, so if I have to arrange this in ascending order, I can say N-paraffin, then olefins, and then cycloparaffin, and then isoparaffin, and then lastly aromatics, correct?
Yeah. This is what I have given here, right? I have already provided this.
Okay, clear. Thank you.
Okay.
Thank you, sir. Thank you so much, sir.
Fine. So it's time up. I stop here. I will meet you tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.